let's look at two examples of epoxide syntheses in this video here. So the first example, we have our alkene molecule. And then we have our MCPBA, metachloroperoxybenzoic acid, as the reagent, and then benzene as our solvent. So all of the reaction conditions to form an epoxide from an alkene. And we're just predicting the product here. So the two carbons that are part of the alkene are where the epoxide ring is going to be in the product. So we have these two carbons, one's bonded to hydrogen and CH2, CH3. One's bonded to hydrogen and a methyl. So that is these two carbons. We'll just call them carbon 1 and 2. Carbon 1 and 2 are where the epoxide ring is going to form. So this here, we've drawn the product. This is the structure of the epoxide. We haven't considered stereochemistry yet, but we will. But this is the connectivity of the product. So now if we're thinking about stereochemistry, we look back to the alkene and whether we have an E or Z alkene and which groups are on the same side of the double bond relative to each carbon. We have a Z alkene in this case. The higher priority group for carbon 1 is methyl. The higher priority group for carbon 2 is ethyl. Those two are on the same side of the double bond. So that means that methyl and ethyl in the product should be on the same type of bond, either a wedge or a dash. In this first structure, I'll just choose to put them on wedges. If you want to put them on dashes, that's fine. We're going to draw both products. So if those two bonds are on wedges, then the two bonds to hydrogens should be on dashes. A little slow here. Okay, so these two hydrogens on the same side of the double bond, so they get the same bond in each stereocenter. Now it's important, I skipped over this, but if we look at, let's say we look at carbon 1. Carbon 1 in the product is bonded to a hydrogen, a methyl, an oxygen, and that longer carbon chain. So that's 4 different groups. We know it's a stereocenter. Carbon 2 is bonded to a hydrogen, an ethyl, the oxygen, and that other carbon chain. 4 different groups again, so we have a stereocenter. If you don't have a stereocenter, you can still draw the wedges and dashes, or you could leave them out. It doesn't matter because it's not a stereocenter. But here we have 2 stereocenters. This product is formed. The enantiomer is also formed. The enantiomer has the same connectivity, but any stereocenter that's an R becomes S, and any stereocenter that's an S becomes R. When we're drawing the molecules, what that means is that any wedge bond becomes a dash, and any dash bond becomes a wedge. So for the carbon on the right, we now have a dash bond to the CH2, CH3, and a wedge bond to the hydrogen. We have a dash bond on carbon 1 to the methyl, and a wedge bond to the hydrogen. These are enantiomers, both products form, and these are the final products for this reaction. Plus, of course, we have the carboxylic acid, but really when we're drawing out these reactions, we're focused on this organic product and not the byproduct. So there's example 1. In the second example, I actually wanted that to be a phenyl ring. We have an alkene, we have metachloroperoxybenzoic acid, and we have benzene. Now we said that metachloroperoxybenzoic acid will create an epoxide ring wherever there is an alkene. in this second example, that will happen only in this alkene that's part of that chain, and not the alkenes that are part of the aromatic ring. Remember, it requires some strong reagents like Lewis acids or strong protic acids for any substitution to happen on a aromatic ring. And furthermore, if we created an epoxide ring off of that benzene ring, that would break the aromaticity even in the product, because we no longer have the double bond where that oxygen is formed. So if you ever have an aromatic ring, we can ignore that for forming epoxides for the specific reaction with metachloroperoxybenzoic acid, and we will focus on that double bond that I highlighted in pink. So that is the bond where we are going to have our epoxide ring. I'll go ahead and just draw in that ring here. And let's number these carbons again. We'll say this is carbon 1 and this is carbon 2. Let's also not forget that we do have a hydrogen on carbon 1. Now those are very rarely shown if we're using skeletal structures, but it's helpful to remember that that's there. So now we have carbon 1 here and carbon 2 here in the product. Carbon 1 is bonded to a hydrogen in a propyl group. We have 4 different groups bonded to carbon 1, so we do have a stereocenter. Let's put the hydrogen on the wedge and the propyl group on a dash. You can switch them. You can probably guess we're going to have both products where the propyl group is on a wedge and hydrogen's on a dash, but we'll start here, hydrogen on a wedge, propyl group on a dash. Now on carbon 2, we have a phenyl ring and a methyl group. Again, we have a stereocenter. To determine which group goes on the wedge, which one goes on the dash, we look back to the starting material. We can see that the hydrogen from carbon 1 and the phenyl group on carbon 2 are on the same side of the double bond. So both of those have the same type of bond. In this case, it is a wedge. And then the methyl group is on a dash there. That's one product. The enantiomer forms as well, where now all that we're doing is changing wedges to dashes, dashes to wedges. So we'll just draw that in quickly here. Phenyl ring is now on a dash. Methyl is on a wedge for carbon 2. Hydrogen on carbon 1 is on a dash, and the propyl group on carbon 1 is on a wedge. Now we have our 2 enantiomer products. Now our epoxides.